pleasure to have you join us for the 2013-2014 Hammond Lecture hosted by the Department of Geography. Many, if not most of you, should know who I am. We do have quite a few visitors and special guests. My name is Derek Alderman. I'm Department Head in Geography. And I'm going to be starting us off, and then we'll be going on to much more talented speakers. I am only in the middle of my second year in this job, although it's felt like 20. And so I'm still learning my way around. One of the things I have learned, and I've learned to come to enjoy, is some of the things that we do right in this department. One of the things that we do right in this department is tradition. And we are not a department that forgets its history. We are not a department that forgets the importance of people who have been here in the past and who have made us what we are. And so the annual Hammond Lecture exemplifies the value that we place on where we've come from. The Hammond Lecture honors a distinguished scholar. We had Dr. Marshall Shepard here, one of the more distinguished people we could probably invite. But this also honors the Hammond family. And Dr. Edwin Hammond, who was a professor and former department head in geography, wish he were around, give me a few tips. And his wife Elizabeth, who was a greatly admired, to put in Kelsey Ellis's term, greatly admired First Lady of Geography. I never had the pleasure of meeting the Hammonds, and I really regret that. They passed away. But I do know that they were a very special part of UT Geography, and they were generous supporters of our program in many, many ways. Every year the Hammond Lecture is a special occasion, but this year is especially important and poignant. Elizabeth Hammond passed away in spring of 2013, and this is the first Hammond Lecture since her death. A picture of her appears on your program. We've included that. If you get the departmental newsletter, we have a very nice narrative about her life and her impact. I encourage you to see that. If you don't have a copy of the newsletter, see me afterwards. I'll make sure you get one. This year's event offers a really important opportunity to reflect on the legacy of Mrs. Hammond and the entire Hammond family. And I've had the pleasure of corresponding with the Hammonds quite a bit the last several months and have enjoyed that thoroughly. Dr. Harden will join us in just a couple of minutes to pay tribute to the Hammonds. This year's Hammonds Lecture is also important because of the reputation and the achievements of our speaker, Dr. Marshall Shepard. Dr. Gracino Mayer will introduce him in a few minutes. He is an accomplished atmospheric scientist. I'm going to go ahead and call you a physical geographer. We got you now. And also president, not so little, president of the American Meteorological Society. Our program has the geography program has a long history of climate research, and the recent hiring of people like Kelsey Ellis, the geographer formerly known as Sheitlin, has allowed us to broaden our expertise in meteorology and natural hazards. And actually there's a very important connection between Dr. Shepard, the atmospheric focus of today's lecture, and Edwin Hammond. Like many geographers of his generation, Ed served in the armed forces during World War II, and he was trained and served in the Navy as a meteorologist. They didn't quite call it that, but he served as a weather officer for the Pacific Fleet, collecting data for his forecasts by flying weather reconnaissance on seaplanes. In fact, one of the Hammond children, Richard, who could not be here with us, told me several weeks ago, I know that Dad would consider Dr. Shepard an especially kindred colleague and would be honored that Dr. Shepard is serving as the Hammond Lecturer. I think we just could not ask for a better fit for this year. I don't know if Marshall has ever collected weather data by flying seaplanes. You ever done that?
Not seaplanes. Some other kind.
Okay. All right. You see how accomplished he is? I thought I was going to get him on that one. But he certainly has done a lot to get here to Knoxville. Marshall braved some very hazardous driving conditions through Georgia this morning to reach us. He very easily could have counseled on us and would have been completely understandable, but he made it here and has made this event very special. In closing, please allow me to welcome the students and faculty at UT, members of the local chapter of the American Meteorological Society, and friends and family of Edwin and Elizabeth Hammond. Please welcome me Dr. Shepard and the Hammond family.
I get to say a few words about the Hammonds, whom I did know, and as several of you did also. So Ed Hammond came to the University of Tennessee in 1970, and he, as department head, he was department head for about 6 years, and then he stepped back as a member of the faculty. He retired in the year 1987. And when he retired, he and his wife, Elizabeth, established the fund, mostly from their own funds, that has supported this distinguished lecture series, and for which we're all really quite graceful. Ed passed away in 2010 at the ripe old age of 91. And then Elizabeth, as you've heard this past spring, passed away at the age of 95. So long lives well lived, and I'd especially like to spend a few minutes remembering Elizabeth, who was actually quite an important part of our geography community at UT. She was born in 1918 and grew up in a series of small towns in southwestern Missouri. Excuse me. She went to public high school, she was an honor student, and she went to the University of Missouri in Columbia, where she earned a degree in English and was honored by being part of Phi Beta Kappa. And I just call your attention to the fact that not every woman in the 1930s went for a college education, and not everyone who went for college education was part of Phi Beta Kappa. So we're dealing with a sort of an unusual and special person to begin with. It was at the University of Missouri that she met Ed. One of Elizabeth's lifelong passions was music. And when she was a student at Missouri, she sang in a glee club, and that's how she met Ed there. Ed always really liked it. He just loved saying that he picked Elizabeth out of a chorus line. And that was, if you'd known Ed and Elizabeth and how sort of distinguished and proper they always seemed, you would find that especially amusing. Elizabeth did teach English for a short time, but she really didn't have a career outside the home for most of her adult life. She did a few jobs when they were first married, and then when they started having a family, she was a full-time wife and mother, but it was almost more than a full-time wife. She was a full-time first lady also. She took her wifely duties, wife of professor duties, really quite seriously. She and Ed were married in 1940, a year after they both graduated, and they moved to Berkeley, California, where Ed was starting his graduate studies in geography. Well, you know, not too long after that, we have World War II coming to pass, Ed becoming part of this naval group. Actually, I think it was when he was in the Naval Reserves. There were several stints. They were separated for various times during the war. And so between the war and then going back to Berkeley for Ed's completion of his doctoral studies, and then Ed's various jobs as a geography professor, they lived as a couple in Berkeley, California, Annapolis, Maryland, Columbia, Missouri, Berkeley again, Lincoln, Nebraska, Badger Village, Wisconsin, Madison, Wisconsin, Syracuse, New York, and then Knoxville, Tennessee. And they had 3 kids, so you could just imagine that Elizabeth had a lot under her charge during this time. The 3 kids were born in 3 different states: Maryland, Missouri, and California, and they were largely raised in Madison, Wisconsin. By the time Ed and Elizabeth moved to Knoxville, the kids were adults essentially. I guess the thing that strikes me about Elizabeth, I think to other women I know of that same era who really made careers out of being wives and mothers and, you know, in some cases first ladies. But I think that she brought something special to it because of her love of reading, her love of books, her love of words, and her love of music. And also, she shared Ed's interest in the natural world, in the physical world. They spent a lot of time outdoors. She was interested in landscapes. Well, their kids became an artist, a lawyer, and a doctor, or artist, lawyer, doctor, and musician. Well, they only had 3, but one of them was both a rock star and then went to Harvard and got a degree and became a doctor. So that was Lawrence. So they had, you know, even more going on with that. Some of us remember that even after Ed retired from the faculty, that he and Elizabeth would host a reception at the beginning of the academic year for the whole faculty and the graduate students. And it was really an elaborate and very nice event. It wasn't like coming to my house where I say there's some drinks in the kitchen, help yourself, and did you bring any snacks? This was, we went, we were given name tags, there was a beautiful spread set out, and somehow it never disappeared while we were there. Things were being put in, people served us. It was really a lovely event, and I think that shows their commitment and how close she was, as well as Ed, to the department. She was such a gracious hostess. As long as they were able, they would always attend these lectures. Elizabeth also, and Elizabeth was right there asking. She was a very intelligent woman, asking a lot of good questions and interacting with our speakers over the years. We deeply appreciate their vision for this series, their generosity, and the contributions that they've made, and also that their family continued to make to help make these possible. So maybe, even though they weren't able to come, I think we could just honor them.
Thank you, Carol. I have never been so excited to introduce a speaker as I am today. Trust me on this. I've introduced quite a few speakers, and I have to preface this introduction, if you don't mind, give me a little leeway here, because I would like to talk about the amazing snow apocalypse that hit, for some reason, seemed to hit Atlanta, Georgia yesterday, and nowhere else, if you've been following this. And anyway, I had to just talk about this, because this caused the governor of Georgia, Nathan Deal, I believe, yes, the quotes that he said to the media afterwards: we've been confronted with an unexpected storm that hit the metropolitan area. Nobody in this room could have predicted it, and we're not Monday morning quarterbacks, and there was just no forewarning whatsoever. And, well, a blog hit yesterday, and you have to read this blog to really appreciate it, and I'm quoting here. Wrong, 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 and wrong. Hammond Lecture, president of the American Meteorological Society, said of critics who allege that the Weather Service botched its forecast, and probably one of the best quotes ever. The buses had a tough time getting kids home, but meteorologists should not be thrown under the bus. By J. Marshall Shepard, and this is true because Dr. Shepard did what he had to do. He came to the defense, and rightly so, for the meteorologists who had it right. That he had it right. They had it right. And in case you've missed it, 2 o'clock this afternoon, I get hit with a CNN breaking newscast. Georgia Governor Nathan Deal today apologized to people who were stranded on the roadways and to parents whose children had to stay overnight. The buck stops with me. This is Governor Deal. Our preparation was not adequate. I accept responsibility for that, and in the future, he will accept offers of external review by outside agencies, such as the American Meteorological Society. Great story. My formal introduction. Originally from Canton, Georgia, which I'm connected with slightly, Dr. Shepard received his bachelor's, master's, and PhD degrees from Florida State University. He was the first African American to receive a PhD from the Florida State University Department of Meteorology, which is, if you're familiar with climate programs and weather programs, it is one of the oldest and most prestigious in the nation. He is an acknowledged leading international expert in the area of weather, climate change. He is currently the Georgia Athletic Association Professor of Geography at the University of Georgia, and Director of the University's Atmospheric Sciences Program. And of course, he is current president of the American Meteorological Society. In 2004, President Bush honored him at the White House with the Presidential Early Career Award for pioneering scientific research. And Dr. Shepard, he has nearly 80 publications in, you have to see the journals that he publishes in. His research findings have been presented over 60 national, international conferences. He's been invited to deliver over 100 presentations at colloquia, briefings, and public venues, and he has a forthcoming book titled The Urban Climate System, and he's co-author, by the way, and I've recently learned about this, with Fred Bortz on a book, a children's book, Dr. Fred's Weather Watch. Create and run your own weather station, available from Amazon for, wow, pretty cheap. $10.95. Wow.
Rich.
That's amazing.
It's not a print.
But I just ordered that book today for my kids, by the way. Anyway, He is frequently called upon by the White House, Congress, and major media outlets, as we've already seen, such as CNN, CBS, Face the Nation, MSNBC, the Weather Channel, and others to discuss weather and climate issues. The title of his talk today is, Can Cities Create or Modify Precipitation, Storms, and Floods? Have we answered this question, and what is next in 2014 and beyond? Please join me in welcoming today's Hammond Lecture, Jay Marshall.
So, if you would need to. So after all of that, hopefully there may be an opening in the department because I may go back to no job at University of Georgia after voting on the day.
We'll take it.
Our governor is not known for certain things. Nice thing about tenure, I suppose. But that was an interesting discussion. As I was driving up here, look, I couldn't help but think, I can't believe it's 2014 in Atlanta. I saw the things that I saw, and there are thousands of cars literally abandoned still on roadways in metropolitan Atlanta. I took a few snapshots as I was coming up here. It's just unbelievable. And we have our American Meteorological Society conference in Atlanta, ironically, starting Sunday, the world's largest gathering of meteorologists in the world. So I'm sure Nathan Dill won't find himself anywhere near the Georgia World Conference. But it's interesting because the theme of that meeting is extreme weather, climate, and the built environment. I set that theme. One of the things that the incoming president of the AMS or AAG does is set a theme for the meeting. And I set that theme about 18 months ago as I was thinking about all the extreme weather that we were seeing in 2011 and 2012. And now nature delivered us a case study for our meeting. So we'll see how that goes. But today, and I modified the title a little bit. That's the title I gave you. But I'm going to talk about how urban environments affect weather and climate, and focus quite a bit on how storms are created and rain is created from cities. But I wanted to frame it in a much broader context here. And this is a picture that I saw on Twitter this summer that I just was taken by it. It's a thunderstorm, and that's Denver, Colorado in the foreground. And if you follow some of the work that I've published over the years, I've looked at how cities can modify weather or create storms. Now, Denver didn't cause that thunderstorm. It's actually in the background. But the juxtaposition of those two images was stunning to me because it really set a nice backdrop for some of the things that I'd like to talk about. So my new title, because I just wanted to give you a broader context, is The Other Climate Change, Climate in Cities. But the focus of it will still be the urban rainfall storm, but I'm framing it somewhat differently. And this is something that happened just a few weeks ago. This is San Jose, California, and you see that low cloud deck, and peeking out in there is the city of San Jose. And many people are familiar with urban heat island. So here's a really nice example of how the landscape is talking to the atmosphere. In that, because of this warm, localized heat center or max, the city, we had a hole in the cloud deck. As you know, clouds and fog is formed as you chill the air to a dew point. So this is a really nice example that sets the stage for this 2014 Hammond Lecture. I'm so honored to be here. I don't know how it is that my name came about, but it's really an honor. As I was looking up Professor Hammond, he, like myself in many ways, he could wear different hats. My degrees are in meteorology, but my work is inherently in geography. So I can wear the hat as a meteorologist when I need to, physical geographer, atmospheric scientist, climatologist. Whatever people want to call me, I'm fine with it because my work has actually touched all of those areas. So. And there are some, if you want to find me, the various places that you can find me. And you can find me on Twitter. In fact, I was just tweeting before we got on here today. So let's just set the stage. Here's a look at the southeast from the SUBI NPP satellite. This is a satellite that was launched very recently for weather studies. And it has a really interesting day-night sensor that allows us to basically see the nights in light. We've had other sensors in orbit to do this. And as I was looking at this, I try to visualize this and I said, boy, this really looks like some type of interesting constellation pattern. Well, there is actually structure in this pattern or in this space. We clearly see Atlanta, Georgia here, various other places that I was highlighting in Georgia for other reasons. And we can clearly see, I bet if you look closely, you can find where we are today. You can clearly see the urban footprint expanding throughout the South. This is not something that's unique to the South. If we look at statistics, we know that urban environments are on the rise, urban impervious surface land cover is on the rise. In fact, right now, we are an urbanized society. More people in the world live in cities than rural areas. By the year 2025, 65 to 80% of the world's population will be urban dwellers. And that's what this figure on the left tells us. This is a really interesting urban footprint diagram by Matt Hartzell, a geographer who actually is a US-born geographer. He's living in China right now, and I've recently collaborated with him. So the various urban footprints of major cities around the world. The reason that's interesting is I've gotten to be somewhat curious about how the shape of a city can impact some of these weather processes that I'll talk to you about momentarily. Well, in some work that I've been doing as a part of the National Science Foundation's long-term ecological research, CalWEDA LTER, I'm one of the co-investigators in that program. We came on board a few years ago, and we took the National Land Cover data set. I just wanted to see what the urban land cover growth around Southern Appalachia has been like over this period of 1992 to 2006. And so here we have 1992, and here we have 2006. And you can see some really interesting things. You can see Atlanta continuing to sprawl. You can certainly see that Knoxville itself has grown over that period quite interestingly as well. But we're interested in sort of the encroachment of urban impervious surfaces into the Appalachian system itself and what the implications of that are for the ecosystem and for the hydroclimate, the water parts of climate. And so I called this in a paper in 2013, and Scott Stofson is working with my colleague Nick Heinen, that has also used this term. I call this the ring of asphalt, because as I look at the Southern Appalachians, we start to see this ring essentially forming around the Southern Appalachia. But the question that I'm posing for new researchers is this ring of asphalt becoming more of a hub and spoke as we start to see that urban impervious surface encroaching into the Appalachian region, and what are the impacts on the water cycle of the hydrologic system? The statistics show that just from our analysis, 15.5% change in hectareacres from 1992 to 2006 in terms of urban land cover. So clearly, Southern Appalachia is even becoming more urbanized. Well, what about the future? Well, this is a look at artificial night sky brightness, light pollution, late 50s, middle 70s, 1997, 2025. This just gives you additional evidence of how our society is urbanizing. And so with that context, what am I going to talk about today? The scale of urban effects, the urban effects on climate, urban effects on weather, mainly the hydroclimate part of weather. A new concept that I just introduced in a paper, and grad students, how many grad students in the audience? Take your notepads out, because I'm going to lay out about 10 PhD or master's theses when I talk about that, because I actually give some ideas about where that needs to go. This is something that we just published. It's a completely new way of thinking about urban climate, called Urban Climate Archipelagos. So here we see the Atlanta urban heat island. This is what most people think about when we think about how cities affect weather. Everybody's somewhat familiar with this notion that because of impervious surface, concrete, asphalt, lack of trees, pollution, cities can be warmer than surrounding more vegetated landscapes, and that's what we see here. But I'm going to introduce to you today a host of ways that cities impact weather and climate, well beyond heat islands. But let me just start off by defining climate and weather. I always do this in almost any talk I give, just because I like that quote I give. But it's important because when we talk about climate change and cold days and snowstorms like we've had now, you'll often have people come up to me and say, Dr. Shepard, it snowed today. What do you guys mean the climate has changed during global warming? I said, well, it's also January. So what we have to remind people is that in winter, in the year 2080, we'll still have winter, we'll still have snowstorms. So weather is your mood and climate is your personality. We cannot base our understanding on climate based on what's happening today or in any given week. So climate is the long-term statistical properties of the atmosphere. I emphasize that because oftentimes we ask people what climate is, they'll say it's average weather. It's not just average, it's the statistical properties. That can be extremes, frequency, and other types of distributions. And weather are these phenomena on short time scales. So With that, let's now embark on this journey to see how urban environments affect weather and climate. Now, this is a paper that we published, Karen Cito, a colleague of mine at Yale, looking at global urban land use trends and climate impacts. And so what we did in this paper, this is really kind of a synopsis paper of the various ways or pathways that urbanization can impact the climate system. And we see that it can impact via the urban heat island, via clouds and precipitation, land surface hydrology, and the biogeochemical cycles, carbon cycle and nitrogen cycle. And then in these various columns, we see the way that actually happens. The bulk of this talk will focus on these two areas, but we'll touch on things like tornadoes and hurricanes because I just think they're cool. And so we want to talk about how urban environments affect those as well. But this is kind of a nice backdrop. So how many of you were familiar with the urban heat island before today? How many of you have heard of the urban dry island? A couple of you have. Cities can actually have an urban dry island as well. So here's a look at dew point forecast from one of our weather models that we use from last summer. And look at Atlanta and look at some of the other cities. You can see that locally the dew points are lower. And this is really reflective of that dry island because cities don't have a lot of trees in them, relatively speaking, as well, which evapotranspire. And so this is just another of the phenomena that the cities can, the footprint that cities can have on the weather and climate system. Well, let's talk about scale. This is one of the things that gets lost in the discussion in urban climatology. Urban effects scale up to impact the larger climate system, but the larger climate system also downscales to impact urban environments. And so it really is a two-way discussion in terms of scale. And so understanding urban environments is very important. I just told you that the Earth is becoming more urbanized. So as urban footprints grow, our weather and climate model resolutions shrink, there's going to be a convergence. So we have to represent these various pathways that urban environments impact weather and climate. Well, let's look at this scaling down problem. This is some work by my colleague Brian Stone at Georgia Tech, that school over there in North Avenue. University of Georgia people do talk to them. This is some work noting that the broader climate change associated with greenhouse gas emissions is causing a certain amount of warming. 97% of scientists who study climate know that. Add in with that the heat island effect. And that leads to something that has been missed. Something that really has been missed. And I'll tell you why. This is from Brian's paper. This is the trend. What Brian did is he took 50 largest cities in the U.S., aggregated the cities and then rural measurements. And what he finds is they both reflect that increasing trend associated with larger scale global warming or climate change. But the cities are warming faster. There's amplification of the warming. Why we've missed this is that climatologists spend so much time trying to make sure that our climate record doesn't have an urban bias in it that we take the cities out. I can't tell you how many times I'll walk up to some guy in the grocery store and say, "Oh, you're a climatologist?" And he's like, "Well, that's just the heat island. The climate's not warming." I said, "Well, actually, the global climate, we usually take that out or adjust for it." I can't believe that people don't know that we don't know that, by the way. But climatologists are pretty smart. But anyhow, we take, I've got other stories anyhow, because in this business, you do these talks enough, you know what's coming. But anyhow, the point is, we've spent so much time trying to make sure we're not accounting for the urban bias, we've missed the fact that the places where we live, 65% of the population by 2025 is warming at a higher rate. That's a critical result. Well, some other ways that cities affect the climate, well, these are not groundbreaking. We know that cities tend to be more polluted from an air quality standpoint. So this is a look at particulate matter or particles in the atmosphere, aerosols, and places that recently were in non-attainment status. That's what the red means. The EPA sets certain standards for pollutants, and you cannot exceed those in a certain daily or aggregate sense. So it looks like Knoxville is one of those cities, or has been. I don't know if you've come out of non-attainment status, but certainly Atlanta is, and here's a look at Atlanta on a typical day in the summertime. So that's another way that urban environments impact our climate system. I'm just kind of walking through some ways that urban areas impact the climate system. Carbon. This is from the Vulcan project. This is where you see red, that's elevated carbon dioxide. So we clearly can see that cities are carbon domes, and not only cities, we see the arteries, the transportation arteries. Steve Holloway and I, a colleague at UGA, we've been talking about how urban domes may have implications for the current boom in urban gardening and vegetation in city landscapes, because carbon actually can seed or be a source for growth of vegetation. We also know from work out of Stanford that these urban carbon domes have public health implications as well. Not only the cities impact the carbon cycle, but they affect the nitrogen cycle too. So we can clearly see that cities can impact the large-scale climate system. That's really what I wanted to kind of get across to you. Now let's come down and scale some. This guy's not looking for enemy aircraft. He actually is stationed outside of Beijing during the 2008 Summer Olympics, because the Chinese were seeding clouds because they thought that they could rain out the clouds before they reached the Olympic venues. This whole notion of weather and rainfall modification. And there are places and countries and even some companies here in the US that do rainfall modification, cloud seeding programs. The peer review literature is inconclusive on it, by the way. As much of many of the clouds that may have been seeded might have rained anyhow. But nevertheless, people still do it. So that's what we call weather modification. But I'm going to talk to you now about rainfall modification that's inadvertent. So consider these questions. What if rainfall intensity was increasing in cities even as stormwater management systems were assuming 1950s rainstorms? Many of our stormwater management systems were designed under the assumption of stationarity. That is, it's going to rain the same way all the time. But we know from various reports and papers that the top 1% of rainfall intensities have increased. And we are seeing that overwhelming some of our urban water management systems. What if you could plan cities in such a way that you could strategically determine areas that would receive more or less rainfall? I'm going to show you evidence that that might be more plausible than you think. In fact, I think it's happening inadvertently. What if rainfall, snowmelt, or other data could be integrated into a smart decision support tool to optimize traffic flow, emergency response, etc.? Atlanta wouldn't be in the mess it's in right now. Seattle's doing that, by the way. And what if I could demonstrate that I could change the regional precipitation climatology of a city without changing greenhouse gases, but simply by changing the urban land cover? These are some of the questions that inform or guide my research. So let's look at that last one. This is from a paper that I published with a colleague back in 2010, a couple of colleagues in Environment Planning B. All we did is took a weather model, a mesoscale model, and we took the current land cover of Houston and ran the model for a typical day, weather day. And we got a typical rainfall pattern. Then we used an urban growth model called Urban Sim and grew Houston to what it would look like in the year 2025. That's what you see there with that outline. And we ran the model with the same weather day from the current day. So the only thing we changed was the land cover, urban land cover. We get the differences there, you see in blue and yellow, that's the differences in rainfall between those simulations. So we changed the rainfall pattern simply by changing the urban land cover. So we have known, and Stan Chagnon and others talked about this for decades, this notion that cities can create rainfall. Well, it's not isolated. This is a look at the papers that have been published and around the world on that phenomena, that cities somehow enhance or create rainfall. The point here being that there are studies from places around the world. We're not cherry picking a city. This is something that has been observed extensively. Where you see red, the finding was that urban environments reduce rainfall. The overwhelming majority of studies suggest that urban environments enhance rainfall in some way. And so we've published a couple of review papers, one as recently as 2010 as well. I know we have my colleague Jay Gullidge is here, and is Willis in the audience by chance? There he is. Willis Shim, my former postdoc, is up in Oak Ridge. You'll find Shim and Shepherd 2009, there's a paper that Willis and I worked on, some other work. So this is not an isolated incident. And I'll say in a moment how it happens, because that's the question that's burning in some of your minds right now. Well, how does the city create its own rainfall? Well, just to give you an example of how the atmosphere talks to the environment, let's see if we can get that to play. You can see over the city of Chicago how the clouds clear more preferentially over the city. Another example. Let me show you an example from Atlanta. This is a radar loop. And that white circle is the fringe of urban land cover in Atlanta. Notice where the thunderstorms in this weather radar image are popping up. On this particular day, the flow is out of the northeast towards the southwest. So on this particular day, you're getting storms firing up over and just on the fringe of the Atlanta urban-rural interface. They're drifting downwind, raining, producing outflow boundary, that cold air that you feel, and those lift and create more thunderstorms. But the forcing to create these thunderstorms is the urban-rural interface of Atlanta. We did extensive work on this to show that. You can see these storms, see them firing up. There was no large-scale forcing on this day, no frontal system. Atlanta, Georgia, is causing those thunderstorms. And it's not isolated. We've seen this over and over, time and time again. Not only can they cause storms, I was giving a presentation in Minnesota, and as soon as I got back to my office, a guy named Kenny Blumenfeld sent me this. He said, take a look at this. This is a squall line, a lot of thunderstorms moving through Minneapolis, being enhanced, he hypothesized, as that line of storms moved over the city. Now, we hadn't noticed that. Most of the focus in the research has been on initiation. But then Deb Yogi, 2012, and I, and a couple of students, and then Shim and Shepherd, in that paper I just mentioned, showed examples that, yes, in our model simulations, an existing thunderstorms could be enhanced as they moved over these urban environments too. Well, let's look at it from a climatological perspective. This is some work by various colleagues, but this figure is from colleague Tom Mode, myself, and one of his students. This is a climatology of rainfall calculated using Doppler radar. So it's a warm season rainfall over an 8-year period. And we see things that we would expect. There's more rain in the mountains because of orographic lifting. There's more rain down in the coastal plain. But focus your eye on Atlanta, Georgia. Over Atlanta and just downwind, climatologically, the downwind area of Atlanta is to the east of Atlanta. That example I showed you was an isolated case. But climatologically, the wind patterns come from the west, so downwind. So notice what we see. Just like we see these mesoscale weather features that we would expect to see in the mountains or in the coastal plain, over and downwind of Atlanta, there's enhanced rainfall. That's interesting scientifically, but that has applications too, because I pulled up the map of where the Army Corps of Engineers is planning to put future water reservoirs, and most of them are out here in the east. Well, if that's real, and we think it is, why not take advantage of that? It's about 15 to 20% more rainfall downwind of Atlanta. There's nothing climatologically different about over here or here. Well, if you don't believe the rainfall, let's look at lightning. This is from Tony Stallings, former UGA grad now at University of Kentucky. He looked at 8 years of lightning flash counts in the warm season. Where you see red is flash count. Where do we see lightning intensities, flashes most prevalent? Over and downwind of the city. Lightning is associated with thunderstorms, convection. Now, when Tony published this, I said, that's neat. I'm glad that we see that because that confirms some of what we've seen in the rainfall data. But I also noticed something else, those little spots of high lightning. I said, what are those? And I started looking around at power plants, and Georgia power plants are near some of those areas. So I don't know if the power plants are seeding convection and producing lightning or attracting lightning. There was a paper coming out, and this is what paper I was talking about with one of Jim Elsner's students, our review, that is looking more into this. Well, I'm gonna give you one modeling example here. This is, let me just give you an idea what this is. This is two model simulations. The two on the left, we took the city of Houston out. The two on the right, we have the city of Houston in. This is a radar image showing sea breeze thunderstorms that happened that day. And this particular thunderstorm here caused a lot of flooding in Harris County that day. We simulated this case. The purple is cloud water. These yellow ISIS lines are rainwater. The lines here represent the low-level wind. So our model simulation is picking out and producing what happened that day. We're getting a sea breeze spot, we're getting thunderstorm. But when we put the city in, we got this particularly intense thunderstorm that we didn't get when the city of Houston's not there. So another case of city of Houston impacting the thunderstorm. So the question, how does it happen? What's the theory? Well, we covered this in several research review papers, but 4 things we think go on. And we don't, and one of the research questions still at bay is, which one is most dominant? Do a couple of these happen? Are there times when only one happens? But one, atmospheric destabilization through thermal mixing and low-level heating. I told you earlier, cities are heat islands. Rising motion. The atmosphere is unstable. That means if you push air up, it'll keep rising on its own if you can make it unstable. Second, increased turbulence and mechanical mixing due to their aerodynamic roughness. Cities have buildings in them. When air blows through a city, or through a stand of trees for that matter, it's mechanical turbulence is generated. That can induce convergence or lift. That's another ingredient for thunderstorms. For basic meteorology 101, in order to get a thunderstorm or rainfall, you need the air to be lifted somehow, you need for it to be unstable or rise, it needs to be moist. So the city is providing some of these ingredients. You also need condensation nuclei. On our planet, clouds cannot form unless they have condensation nuclei, or CCN. Just can't happen. We can't achieve cloud condensation without a nucleus. Cities are polluted, they're dirty, or so they're sources of pollution. But that's a mixed bag. I'll say something about that. And then 4, Bob Bornstein and colleagues have talked about this notion that as thunderstorms approach cities, either because of a thermodynamic bubble or a physical bubble, they sometimes split, bifurcate. We've shown that. So let me just give you quick examples. Destabilization, the city is warmer, so we have in meteorology something called a lapse rate. That's how the temperature changes as we go up. So you get a destabilized profile, so the air will want to rise. Cities cause convergence. If you don't believe me, take a look at this. That's Panama City, Florida, a couple of years ago. In this case, we had a fog bank, and we see the condos lifting the moist air. And that happens also with air that's laden with water vapor that maybe hasn't reached the dew point yet, or the condensation point. So there's proof that buildings lift air. It's one of the ingredients we need. The role of aerosols is unclear. This is a paper by my colleague Danny Rosenfeld in Science. Aerosols are needed, but the current thinking is if clouds are too polluted or dirty, it proves there's too many small cloud drops that aren't able to grow to become rain. So aerosols actually suppress. But there's an alternate theory that says, well, that suppression can happen, but if there's enough low-level forcing from something else, the rain was suppressed, so you didn't get the downdraft blowing the storm out, so you can invigorate the storm more and get more rain. The jury's still out. But let me show you an example of how aerosols are important for precipitation. Now, by show of hands, who has ever tasted a snowflake with your tongue? Almost all of us have done that. Would you have preferred it to be beef flavored or pork? What I mean by that is this. This is a case that Tom Mote and I published in an IEEE magazine journal called Earthzine, of a case of snow that was produced in a little narrow band. This is a satellite image of the snow cover. Dodge City, Kansas. That's a little band of snow that was produced on a given day. That's the radar image up there, so that light blue is a snapshot of the plume of snow. That snow was caused by slaughterhouses, emissions from slaughterhouses seeding the clouds on that day. There was a fetch of air coming out of the southeast, positioned in such a way that you're getting effluent or emissions from those slaughterhouses. There was water vapor from power plant. And so we got this little narrow plume of snow. It was odd. So I saw it, I was like, okay, I immediately emailed the National Weather Service office that put this on their website. I was like, give me everything you have on that. And so we wrote a little paper on it. So that's just an example of how seeding can influence rain, or snow in that case. And then Bob Bornstein and colleagues have shown that a large thunderstorm can approach a city like New York and bifurcate, split, and in some cases come back together. Now I have a theory on this. I'm about to give someone a really nice thesis topic, but it's a somewhat theoretical one. No one's really explained why this happened, but I saw just enough of a hint in it in one of my graduate students' thesis that I came up with an idea. I haven't proven it, I haven't looked into it yet. But here's a satellite image of flow in the ocean. There's an island there with a mountain. The flow is coming out of the northwest. On certain days, that flow impinges upon that mountain and induces these wave-like features in the cloud, which we call von Karman eddies. We know that this happens. Physicists can reproduce this in the laboratory. Not only do we need to reproduce, I see it all the time in satellite imagery. Are cities acting like that elevated source in some way to produce these von Karman type eddies that would lead to bifurcation? I don't know the answer to that, but that's the hypothesis. So that's the rainfall. So let's move to a different part of how cities affect weather and climate by saying, are urban floods increasing? These are just flood cases that we've seen in the last few years, most recently in Boulder, Colorado, Nashville, Atlanta, Mumbai. So one of the places that we have a pretty good understanding of how cities affect hydroclimate is in flooding. Well, this is going to be in the new National Climate Assessment Report. Percent change since 1950 in the top 1% of the heaviest rainfall events. In other words, the heaviest rainfall events are getting stronger in every region of our country. That's going to be published in the next National Climate Assessment. That's what I meant earlier when I talked about cities being designed for 1950s rainstorms, not 2014 rainstorms. This is a paper we published in the Bulletin of the American Meteorological Society diagnosing the 2009 Atlanta floods, which we see produced just amazing rainfall totals. Atlanta's had some bad luck over the last 7 years. We had a tornado, we had a serious drought, maybe 2009 floods, and now a 2-inch snowfall. But anyhow, the 2-inch snowfall is not the issue. It's the fact that there's a socioeconomic driver behind that we're seeing in many of these high-impact weather events. So that was, we looked at that. And so the bottom line is the urban water cycle is very different than the natural water cycle. There's much less infiltration. In other words, when it rains, not much water is going into the soil. And because of this, there's more runoff. And so cities are already natural perturbers, if you will, of the hydrological cycle. And you add into that the possibility that we're seeing more rainfall because of them. I don't think it's by accident that we're seeing an increase in urban flooding. Well, what about tornadoes? Josh Warman, if any of you watch Storm Chasers, probably have seen him in that episode. He notes that the aerial extent of cities and surrounding populated areas is growing, as I've stated earlier, and that someday a large tornado will track through a densely populated urban environment. Tornadoes going through central business districts of cities used to be quite rare. NOAA actually has a website, and there weren't very many at all. In the last 10 years alone, we've seen quite a few, including Atlanta. And so this is a really nice paper by Josh. Well, let's look at tornado tracks over the past 56 years. And this is a dissertation question. I would ask this on a prelim, because there are a lot of things you can ask about this. First of all, tornadoes clearly don't happen very much in the western United States. We know why, right? Well, you don't know why. It's because there's not a real good clash of air masses out here. This is a real good place where air masses from the Gulf clash with air masses coming out from the polar regions. Anybody from West Virginia in here? Not a single person? At all. Well, clearly tornadoes don't like West Virginia either. Yeah, so, no, it's not the case actually. It's just the fact that the radar and observations aren't there. The tornadoes are happening here, we just don't, people either aren't seeing them, and more today, tornadoes are indicated by Doppler radar. So this gives you a real nice look at the distribution of tornadoes. Here's Dixie Alley. A lot of people know about Tornado Alley, but literature is showing us more and more that there's a little pocket called Dixie Alley. What's worrisome about Dixie Alley is because of the socioeconomic profile of people in Dixie Alley. Poor people here, substandard housing. Houses out here are designed for tornadoes to some degree. So we lose a lot more property in life in Dixie Alley. Walker Ashley, one of Tom Oak's former students now in Northern Illinois, has talked extensively about that. What about storms that produce at least $50 million in damage, a tornadic storm? Well, I show this to make the point that I think a lot of those are in urban areas because there's a lot more stuff to destroy that costs. So kind of keeping with our theme of urban environments affecting climate and weather and implications of that. So let's just use Atlanta, 74 to 2005. This is from the College School of Georgia's land cover. The dartboard is getting bigger for the tornado. So of course we're going to see more urban influence or urban impacted tornadoes. I mean, part of the reason we didn't see as many tornadoes affect the cities is just a chance thing, and it's just a smaller area. But now it has more likelihood of hitting the area. Okay, so let's shift gears here because we're talking about ways urban environments affect weather and climate. Hurricane Sandy. Talking about tropical system now. One of the reasons Hurricane Sandy was so devastating is that it affected one of the most populous regions of the United States. Blue is the inundation. Red is the population density. Let me remind you that Hurricane Sandy, or Superstorm Sandy as it was called, was barely a Category 1 hurricane. Just like this storm in Atlanta was a 2-inch snowstorm. So it illustrates something that is important for students and all of us as scholars to keep in mind going forward. It doesn't take the mega event anymore because of this convergence of the event itself, population, and infrastructure. So there are real social science questions at those intersections. In fact, here is a nice paper by Barry Kime out of LSU looking at recurrence intervals of how often a hurricane visits different parts of our coastline. If you look up there at New Jersey, for all hurricanes, that part of New Jersey doesn't see a hurricane. I mean, the recurrence interval is about 1 in 105 years. So clearly an extreme event. But when it hit, because there's so many more people there, so much more infrastructure, it's a problem. It was barely a Category 1 storm. Getting on a soapbox here for a little moment. This is why I have a problem with this notion when we have storms forming. I'll get questions like, is it going to be a Category 3 storm? Media loves to ask, is it going to be a major storm? It doesn't have to be a problem. So then, sort of as I draw to a close, this notion of megalopolis is something I've been thinking a lot about lately. French geographer Jean Gutmann's book Megalopolis described the urbanized region from Boston to Washington as the megalopolis, very large city from the derived Greek origin. In contemporary times, it has a similar meaning. Oxford Dictionary of Geography describes a megalopolis as a many-centered, multi-city urban area of more than 10 million inhabitants. Remember I said earlier that we have a 2-scale problem. So I've become interested in whether megalopolises have an impact on our climate. So if we look back at this image of the United States from satellite, I see many, M-I-N-I, megalopolises emerging. Many smaller megalopolises emerging. I think this is becoming one. We already know about that one. Right? What about this? So my theory is that in the same way that we know that one mountain can affect weather by producing clouds and rainfall, we know a chain of mountains has a different spatial impact on weather and climate. So we know urban heat islands from one city has an impact on weather and climate. I am framing these things as urban climate archipelagos and inviting us to think about the ways that a network of cities impacts weather and climate differently than an isolated city does. So we published some work just recently in Earthzine, and we have another paper that's coming out in Journal of Applied Meteorology and Climatology. We've been looking at the megalopolis from Richmond, Virginia, up through New York City, and doing some of those modeling simulations. And what we found, we did a couple of case studies, and they all showed the same thing. When we take the megalopolis out of our run, the urban land cover, that storm system develops differently. It's a much heavier rain system when the city landscape with the megalopolis is included. But urban climate archipelagos is not just about one phenomenon. That's why I didn't call it urban heat archipelago, call it urban climate archipelago, is I'm inviting us to think about the ways that this network of cities affects the climate system. So here are those starter questions for those grad students. In that paper that you could Shepherd et al. 2014, these are a list of the questions that I've posed. I don't have answers to them yet. They need to be explored. I do have a PhD student that's starting to look into some of these, but what are the space? I haven't even really defined what an urban climate archipelago is. I presented a definition of what it is. Are there different classes or subdivisions? What are the regional and global distributions? What are the thermal impacts of urban climate archipelagos, et cetera, et cetera. And they're touching different aspects of the climate system. So I would invite you to take a look at that. I'm going to skip through these second two because I was just making the point that, since I was here in the Appalachia region, we're actually thinking about many of these questions that I just presented from the context of Southern Appalachia. So that's really what this research is about. So in two final slides, this is one of them. So I've told you about the ways that the urban environment affects weather. I've told you about the ways that the urban environment affects climate. And I've tried to hint along the way that humans live in cities, and so there's vulnerability. This is some work by my graduate student, Anita KC, 2013. We've developed a climate vulnerability index. And in that climate vulnerability index, we're trying to capture overall long-term climate change, increases in hazards like drought, floods, and heat waves, plus social vulnerability that Susan Cutter has talked quite a bit about over the years. And so when we did that for Georgia at county level, you can see the trends in our climate vulnerability index. And so what you see is that the most vulnerable counties in Georgia, and increasingly becoming vulnerable, are the urban environment, our urban counties, and our coastal regions too, by the way, for different reasons. So there are social implications that I'm always thinking about. I'm not a physical scientist who just thinks about physical problems. So in closing, that's why I was recently on this National Academy of Sciences panel that produced a really nice report, booklet. You can get it free at the National Academy's website, Urban Meteorology. And we talk about the science of urban hydrometeorology and urban meteorology, and then how we can make that information actionable to stakeholders, planners, public health. And so I invite you to take a look at that report because it really tries to close the loop on the science and the societal implications. And with that, I'll close. Thank you. Time for a couple questions?
Dr. Shepherd, I'm sure you'll take a few questions.
Absolutely. Yes.
Any questions, Dr. Shepherd?
I'm thinking about here when you're showing the urban-rural interface
Yes.
between the two, and you're showing essentially orographic effects from these cities where essentially you show, your concentration has been on the precipitation, and I'm a drylands scientist, and so I got really interested in the rain shadow
Right.
on the other side. And has any work been done looking at that?
Not a lot, but one of the things that we've attempted to do, we've got a grant from NASA to look at sort of urban water budgets, and so one of the things we're trying to do is look at sort of this notion. I often get the question, so because there's sort of preferred regions of rainfall caused by the cities, it's sort of robbing rainfall from another part. And so I think a water budget study is going to tell us something about that process, but we've got to the way we design our budget study region is going to be important. There are a couple of field campaigns that we're participating in with NASA where we're going to really help design that. But it's really early work. But yeah, I think there is kind of an urban range here. Absolutely.
Do you know if anyone's taken a look at this, say, using GRACE?
No, I think the scale of the GRACE, by the way, is a satellite system. It's a really cool. I teach a satellite meteorology and climate course at Georgia. GRACE is these 2 twin satellites that are moving in orbit right now, and it's very sensitive to small changes in gravity, Earth's gravitational field, and that can be related to changes in water, in the water system. And so that's when I thought I should take the time to explain GRACE. So GRACE is very useful for a lot of hydrologic or snow mass balance and other types of applications. The scale of some of the urban work that we do, I'm not sure. I think GRACE may be a little too coarse, but I don't know. It might be worth peeking at. Because it tends to be more larger scale problems. Other questions? Comments? Yes.
Carrying right along with this, I'm actually interested in the possibility that not only is there possible robbing of moisture in one area, Robert's question, how about these lightning storms?
Yes.
If you're getting a lot of lightning storms in the urban or urban fringe, are you not getting the lightning storms, say in the foothills of the Smoky Mountains or someplace else? Have you actually changed potentially lightning distribution, or can you just have more overall with lightning?
Well, in Stalin's work there, it looked that there was less lightning occurring in some of the orographic regions. I mean, it's sort of the mountainous regions. And that was actually one of the questions I had. I said, I just can't believe there's not as much lightning happening in these storms. But some of the microphysics, I think there are questions that need to be answered, because what we know, in order to get lightning, you need glaciation. You need a storm to get some ice in it. And so, for example, when I was the deputy project scientist for the Global Precipitation Mission, which is launching next month by NASA before I left NASA. And the predecessor to that mission was the Tropical Rainfall Measuring Mission, or TRIM. And from the TRIM lightning sensor, we found, for example, that thunderstorms over water, over the oceans, have much less lightning over land. So in other words, when we plotted a lightning climatology for the globe, people start saying, where's the lightning? We know there are thunderstorms out over the ocean, but where's the lightning? And it turns out that because the updrafts in these land-based storms are stronger, the process of glaciation is faster and more efficient. The question is asked then, are there different glaciation mechanisms in these sort of orographic storms because of the base of these storms and other things that may be at play that are limiting lightning formation? I think the data hints at that, but I think your question, Sally, is very important and a good one. I think it's something that I personally haven't looked into, might be something worth looking into if we get our next 5-year round of funding where our Coweta LTR, we're in the renewal process right now. And we are forming our research questions. And I'm the person on the team looking at hydroclimate and weather and climate impacts in southern Appalachia. So
The reason I ask, and you probably realize this, is that lightning frequency is one of the things that people like myself and Henry who think about fire history, people are always asking about lightning. And 201, every single person will use today's lightning pattern to tell me what lightning could or couldn't have done 300 or 1,000 or 2,000 or 10,000 years ago.
yes.
And I don't have the background you have, but it seems to me that just like other things in the world have changed, we shouldn't assume that you could say there's very little lightning today, therefore there wasn't more lightning, say, before we had urbanization.
Absolutely, and that's one of the, I'm glad you make that point, because that's exactly right. You know, oftentimes we look at these changes on scales, synoptic and global scales, but these are what I call mesoscale or regional scale phenomena, and we know there are changes. But these are things that the literature is just now starting to reveal, and so with that backdrop of knowledge, then it makes sense to say, okay, we need to go back and look at lightning distributions, and this is where I should talk to you folks, because what are the proxies for lightning? Can we match up lightning, contemporary lightning from lightning data that we have from things like the National Lightning Data Network or from the Lightning Imaging Sensor with contemporary kind of proxies that you all use, and then go back and then compare those to climatologies in the past? I think that needs to be done, if it hasn't been. Other questions?
So what are the implications for urban landscapers? I'm just wondering, because we are a landscaping company, and is more green better?
Well, that's a great question. I was talking to someone at lunch about that today. By the way, I'm going to answer your question, but I had lunch with the local chapter of the EMS. If anyone here is interested in the local chapter of the American Meteorological Society. The president, wave your hand, is right here. And they have meetings every other month, I think, or so. And so it's just, anyone's open to join.
Let's give her a name. This is Dr. Joanne Logan.
Yeah,
She's
Dr.
a longtime
Logan.
friend of
I couldn't
geography,
remember
but
your
she's
last
not in
name.
our department.
Dr. Logan actually has been a gracious host to me today, and as well as the geography department, met me for lunch. So, but getting back to your question about landscaping, one of the things that we know, particularly for mitigation of things like the urban heat island, is that there are certain preferred greening patterns. So, for example, in Atlanta, there's something called Tree Atlanta. They try to plant trees all over Atlanta to reduce the urban heat island through increasing evapotranspiration and shading. But what we know from the literature is that you can't just put trees anywhere in Knoxville. There's certain strategic patterns that are more conducive to cooling. And so I think there is, from a sustainability standpoint, if there is a significant heat island issue here, a heat stress issue related to the urban heat island, I think that there is some literature that can guide the way you consider landscaping, for example, in cities. Also, not just from the standpoint of evapotranspiration, but shading as well, strategic planting of trees and whatnot. But I think there's another challenge. For example, Georgia, our department in Georgia, we have a green roof. Have had it for decades.
That was my tree ring lab, yeah.
Absolutely.
Yeah.
Merle Prunty and others had vision well before it was kind of in vogue to do for LEED certification and all that kind of stuff. And so you can sort of cool rooftops, and that has implications, but it also has implications for things like water storage in urban environments too. Vegetation has implications for the urban water budget that I showed as well. So I think there are a lot of things that landscapers can think about.
In order for a city to have the orographic implications you're referring to in the latter half of the lecture, or a string of cities, do they have to be a certain height, or is it the very fact that they are small?
Excellent question, excellent question. Colleague Devna Yogi and his students Paul Schmid have a paper in Geophysical Research Letters where they're looking at what size does a city have to be to have this rain effect. And so they found that the diameter of a city has to be at least 20 kilometers for it to see a discernible impact on cloud and rainfall processes. Now, the interesting thing about that is, as we're starting to see what I'm calling these urban climate archipelagos, you get sort of a magnification effect. And so, does that have even more impact on things like rainfall or heat stress or whatever your climate variable is that you're interested in? I mean, this is still very new stuff in terms of urban climate archipelagos, just starting to think about. But one thing I will mention to follow up on the second part of your question, and this is why I'm interested in sort of the three-dimensionality of cities and not just a blob that is an urban land cover. I think, for example, Washington, D.C. would have a very different effect on the environment than Atlanta does, because Washington has low-profile buildings. Because I've lived in the Washington, D.C. area, I think buildings can't be taller than Washington Monument or something. There's some kind of zoning law. So very low-profile buildings. So that second term, I put those list of 4 hypothesized reasons the urban environment can make a thunderstorm. I think that second term may be somewhat minimal for a city like Washington, D.C. Chandana Mitra, who I know that Sally and I were talking about earlier, did some work in Calcutta, India. And Calcutta is a very linearly organized city along the Ganges River. And so depending on the fetch of the wind, there's not much of the city to blow over, so to speak. So that's why when I put up those urban footprints, I think I'm now getting more interested in shapes of cities and the three-dimensional morphological parameters of cities. We have a paper published in Journal of Atmospheric and Oceanic Technology 2011. Michael Carter is the lead author, looking at, we changed the morphology. We use LiDAR data, lasers flying over a city to tell us what the buildings are like in Houston. And then we found a way to put that into our land surface model and looked at the impacts of the scale of the building size as 3 dimensions. We dabbled with that, but not a lot.
Let's please join me in thanking Dr. Sheriff. I'm a bit of a geek, but this guy's a huge deal. And I got you a little program sheet. Might want to go here and get a little autograph. But I do appreciate you coming. And again, I want to thank the department for all their work.